how to derive the velocity of a wave on a string. For this we do a simple experiment. We take a string of length L whose mass is capital M and one end is fixed and the free end is moved up and bring back to the original position. Then one pulse is created. Say at time t is equal to 0, pulse is at origin. After time t, this pulse will travel to the forward direction, say with velocity v. We have to find out the expression of v in terms of the physical property of the medium. As we have studied the longitudinal waves and transverse wave, the velocity of the wave depends on the physical property of the medium. So for this, for the finding the expression of velocity, we can use two concepts. One, we will use circular motion concept. And second, we'll use Newton's law of motion. Newton's second law. So for second method, we'll use Newton's second law. So first we will try with circular motion concept. Now the question is how we can use circular motion concept. When this pulse is created, दो चीज़ें हो रही हैं. एक, ये पल्स का फॉर्मेशन हो रहा है. दूसरा, ये पल्स फॉरवर्ड की तरफ v स्पीड से मूव कर रहा है. तो अगर हम वेव के साथ मूव करें, यानी ऑब्जर्वर अगर वेव की स्पीड से ट्रैवल करे, तो ये पल्स हमेशा ऑब्जर्वर के सामने होगा. मीन्स दिस पल्स विल बी एट रेस्ट विथ रिस्पेक्ट टू द ऑब्जर्वर. And then whole string will be moving backward with speed v. Means if the observer is moving on a trolley, say if you take observer on this trolley and is moving with speed v, same as the wave speed, then this pulse will be at rest. Pulse will be at rest with respect to observer. And whole string will be moving backward with speed v. And a string will be moving backward with speed v. Then a string element on this pulse will be moving backward with speed v. So now we can apply the concept of circular motion as the element of the string is moving on this arc, which is a part of maybe any circle of radius r. So we can apply the circular motion concept. This pulse is stationary with respect to the observer, and a string element is moving on this arc with velocity v at the backward direction. So things to remember, we are taking a reference frame which is moving with speed v, which is same as the wave speed. So now if we take a small portion of this pulse, say AB, and I'm going to enlarge this one. This is the element of the string AB. Now I'm going to analyze the forces on this element. क्या क्या फोर्सेस के ऊपर लगेगा? एक एंड पे फोर्स होगा टेंशन T, दूसरे एंड पर भी टेंशन है T. One more thing, we are assuming T is constant throughout the string. T will remain constant throughout the string. See, when disturbance is created in the string, because of this disturbance, there is elastic nature of the string. So length will increase. So tensor will change. So tension will not be same throughout the string. But we are assuming tension is constant throughout the string. This will only happen when amplitude of oscillation will be small. So for small amplitude of oscillation, we can assume tension will remain constant throughout the string. So now we analyze this element AB. Say this element is a part of any circle whose radius is r, and this element is making an angle 2 theta at the center C. This radius is r. If I resolve these forces, this angle will be theta, this angle will be theta. So along x direction, this will be t cos theta, and vertical component will be t sin theta. So forces along x direction will be 0. This is positive and negative sides, it will be 0. And net force in y direction will be t sin theta is 2t sin theta. As we have taken the element is very small, so theta will be very small. So for small value of theta, we can write sin theta is equal to theta. So this will be 2t theta. This is Fy. Equation number 1. And from this arc, we know the relation 2 theta is equal to, say AB length is delta L. We can take length of the arc AB is delta L. 2 theta will be delta L by R. So we can replace 2 theta value in equation 1. So we get Fy is equal to T delta L by R. Now we have analyzed the forces on this element AB. As we know, the net resultant force on the element is Fy. So we can find out the acceleration of this element. Ay is equal to Fy by the mass of the element. Mass of element. Fy is T delta L by R, and mass of the element will be mu times delta L. So you can substitute the value T delta L by R mu is already, we can cancel out delta L will get cancelled out, so we know, so we get the value of Ay as T by mu R. This is the acceleration of this element, T divided by mu R. So we calculate the value of acceleration of the element in vertical direction. Now, with respect to the observer, the element AB is moving on this arc with speed v. So centripetal acceleration, so I can write this element AB is moving on a circle of radius r with a speed v. So centripetal acceleration will be v square by r. So ay will be equal to ac. Say this is equation 3 and this will be equation 4. So from 3 and 4 we have v square by r is equal to t divided by mu r. R will get cancelled out, so we get v is equal to t by mu square root. So we got the expression for the velocity of the wave on a string. See, the velocity depends on the tension, which is elastic nature of the string, and mu, mass per unit length. It's the inertial property. So it depends on the elasticity of the medium and the inertia of the medium. It does not depend on the wavelength, frequency. This parameter is not coming in this expression. So v is equal to square root of t by mu. We can write this as v is equal to square root of t. Mu we can write m by l. This will be divided by m times l. So if we increase the tension in the string, velocity will increase. If we increase the length of the string, keeping mass constant, then velocity will increase. If we keep the length constant, and if we increase the mass of the string, means heavier string, then velocity will get reduced. In the next video, we will derive this expression using the concept of Newton's second law. Thank you.